video, we are going to be talking about the angle bisector theorem, and before we actually solve a problem involving the angle bisector theorem, we're actually going to 1. Explain what the angle bisector theorem is, and 2. Prove the angle bisector theorem, because I am a huge fan of proofs. And I'll be honest, I don't actually, well, let's just say that there are some math concepts that you will forget along the way. If you're in the middle of learning calculus, you're never going to need to know the angle bisector theorem. But if you remember the proof and you remember how you got to the theorem, and you remember, oh yes, this is a theorem that exists, well, you don't actually need to memorize the formulas in the first place. So let's say we have a triangle here. We're going to label this, I'm going to label the vertices A, B, and C. And we have an angle bisector. So what an angle bisector means is that it bisects this angle here into two congruent angles. So these two angles are congruent, and I'm going to label this point D. What the angle bisector theorem states is the ratio of AC here over CD is equal to the ratio of AB over BD. Now you're thinking, wow, this sure looks kind of like something interesting that we see all the time, like maybe similar triangles. Except the issue here is that we can't actually prove that ACD is a similar triangle to ABD. We just can't. We don't have enough angles. And I'm not sure if you guys learned this anymore, but there are a few ways that you can prove that two angles are similar, but the easiest way is through angle-angle similarity. I'm not sure, yeah, angle similarity. What the tilde is on 1 point, but anyways, angle similarity, and that's what we're going to use to solve this. Except, like many of our proofs, we have to draw a few extra lines in order to prove that this is true here. Well, the first thing we can kind of do here is that we can extend this line here, extend AD, so it looks kind of like this, and I'll call this point E. And then I'm going to define a line. We'll define a line BE that looks like this. And I'm going to define it to be parallel to AC. And I make the rules, right? I made up this line BE. I have defined it to be parallel to AC, like so. So these two lines are parallel. And the interesting thing about this is that the reason why we made parallel lines is so that I can state that a few other angles are also congruent. You'll notice here, this angle here and this angle here, if you kind of squint and you kind of try to visualize it, you'll see that there are alternate interior angles with the transversal AE and the two parallel lines AC and BE. So we can mark this as congruent. Oh, first I should use a different color to mark my angles. So this angle is congruent to these two angles here. And, well, we know that these two angles here are congruent. The interesting thing about this is that when you have two congruent angles in the legs, you know that this is an isosceles triangle. ABE is an isosceles triangle, and this is always true, by the way. If you have an isosceles triangle, the leg angles are congruent. If the leg angles are congruent, it's an isosceles triangle. So we can mark these two as congruent. Another thing we can do here is we can mark vertical angles. These two angles are congruent. And you'll note that AB is equal to BE. The reason why I mentioned that is because I'm going to make a note here that you can also replace AB with BE. Okay, moving forward. Now you have two similar triangles here using AA, angle-angle similarity. So these two angles are congruent, these two angles are congruent, thus we can say that ACD, and you have to be mindful about where your the order of your letters when you're writing these similarity statements. Triangle ACE is similar to triangle EBD. Okay, well now that we have this, we can conclude this part here. So AC, so these two letters over CD, so these two letters, is equal to EB. Oh, sorry, did I write this wrong? These two letters, A, C, D, C, D, these two letters, E, B, D. Yeah, I did write this right. Okay, well, AC over CD is congruent, AC over CD is equal to EB over BD. Oh, and, well, I guess I wrote this in the opposite way. I should, okay, well, I can actually, EB is equal to BE, of course. And so, because BE is equal to AB up here, we can also write that this is equal to AB over BD, which is exactly what we wanted to prove in the first place, proving the angle bisector theorem. And you'll notice that by the end of this, we didn't really use the letters down here like D and just E. We use this as a mechanism to figure out this part here. And we drew some extra lines, made some isosceles triangles, made some parallel lines. I'll say that this, don't feel bad if you don't get this proof right away. It's something that someone has to teach you. It's difficult to figure out proofs by yourself, honestly. So this proof is relatively simple, but the genius idea that led to this proof was, drawing a parallel line here. Okay, well, we're actually going to use the angle bisector theorem to solve problem 4. Okay, problem 4. In triangle ABC shown here, segment AD bisects A. AB is equal to 30, BD is equal to 10, and AC is equal to 51. And how many units long is side BC? So now you're going to learn how to use ratios to figure out certain sides. We have a triangle that looks like this. Down here, these are congruent. We have A, B, C, D. We know that AB is equal to 30. BD here is equal to 10. AC is equal to 51. We're trying to find out what BC is. Okay, well, we can call DCX here. So according to the angle bisector theorem, we have 30 over 10 is equal to 51 over x. Well, 30x is equal to 510. X is equal to 51 divided by 3, and it is divisible by 3, because 5 plus 1 is 6. 3 goes in there once, 21 sum to, x is equal to 17. Except we're not trying to figure out what x is, we're trying to figure out what BC is. So if we know that x is equal to 17, 10 plus 17 is equal to 27. 27 units. And this is kind of a practical application of the angle bisector theorem. I will see you guys in the next video where we talk about the Pythagorean theorem and special right triangles.